real necessity is a wonderful knockout.
Okay.
Gives you a little bit of drugs.
So, what questions does anybody have? Has everybody looked at the review sheet? No, not really. Did everybody see that there is a review sheet?
Yep.
Okay. So, I don't have any particular wisdom to share with you today. It's entirely up to you.
Any words of encouragement? Any affirmation that you can give us?
How's the Q hit?
You can do it.
Yes.
They're going to be more vocab on this test compared to the last test.
No, there'll probably actually be, there'll probably be less of that. It's just the point that you have to know vocabulary. So things like, for instance, if I said something about a eutectic reaction, right? You have to know the vocabulary in order to be able to do the problem. So the vocabulary here is going to be more about that kind of stuff and less about.
So all the problems are quantitative?
All the problems are quantitative. Most all the problems are quantitative. There's some that are not.
Eutectic is where it goes from liquid to solid, right?
Eutectic is where it goes from liquid to solid. Eutectoid is where it goes from solid 1 to solid 2.
Okay.
Or solid 2 to solid 3, actually.
What is the other one?
Sorry. You had to sit next to Jesse.
I totally
Sorry. Anyway, so that's how the vocabulary is primarily being used in the context of the problems.
So
So is it
you
like
have
that
metals,
flush,
ceramic polymers, composites. How are those going to be turned into like math problems, I guess?
So as we slide down to the section on metals, ceramics, polymers, and composites,
Let's see it.
we can see that you need to know the naming conventions for the most common metal alloys.
For what kind of problems?
I'm just saying you need to know, I'm not going to tell you the problem, I'm just saying you need to know the naming conventions.
So like a
So
sentence
there
about-
are, I mean, I'm not necessarily saying this is a short answer, but I'm saying there are some short answer problems, yes. But you need to know, so like, you need to know, for instance, a 316 steel, what is that?
No idea.
Piece of steel is 3/16 thick.
No.
Alloys.
It's a stainless, so you need to know that that's an austenitic stainless steel.
Oh yeah, there it is.
If I said, what's 1080 steel?
Stabilized by nickel.
What's 1080 steel?
10%.
Somewhere here.
Nickel, 80% iron.
No.
No. Plain carbon.
It's a 10 means a plain carbon, and 80 is the point, so it's 0.808% carbon. Okay, so those are the kinds of things that I'm talking about when I say know the naming convention. And it's mainly just the steel and aluminum alloys that would be of interest. And obviously I'm not going to ask you all of them. So just be familiar with those. Right? So what are the primary alloy constituents for the most common metals? You need, if I ask you what is brass, you need to be able to tell me what brass is a mixture of. Right? It's a mixture of what?
Copper, zinc.
Okay, the main, I was looking for the main alloy constituents. I don't have to have all the minor.
Oh, so that's it?
Right. So that would be fine. There's different, you could say there's also copper tin, there's copper, there's other different bronzes, that sort of thing. In ceramics, we used to talk about really three things: ceramics, glasses, and glass ceramics. So you really need to be able to distinguish between those. Polymers, we have different kinds of polymerization. What are the two kinds of polymerization? No, the polymerization is how we make them.
Oh, chain growth and
Linear?
step growth.
So addition and condensation, or chain growth and step growth are the two choices. Polymer structure, so you have branching, cross-linking, different ways of structuring the polymers, right? Linear versus network polymers, that kind of thing. Quantified chain length. So remember there were two ways of quantifying chain length? You remember there was an RMS chain length and an extended chain length. Remember how to do those two? If you don't, look it up. understand the key differences between thermoset and thermoplastic polymers. So those are the two broad categories of polymers.
That one becomes squishier in high temperatures.
Right, one softens at high temperatures, one hardens at high temperatures, yes. Composites, so there's 4 types of composites. And then we quantified isostrain, isostress, and aggregate conditions. Remember that? So,
Do you have special conditions, or is that the combination you use?
special conditions, what do you mean?
Like, we went over the conditions for.
Isostrain, isostress,
Yeah.
and then I had aggregate, and I said when the aggregate is higher matrix, or higher modulus than the matrix, or when aggregate was a lower modulus than the matrix, you get 2 different values at the end for that.
So, but what is would that be constant? Would it be a combination of isostress and isostrain, or?
So weave, yeah, weave, you can't really do that with, right? And then materials processing, just, know the various categories. Okay, so this last section here is all knowledge, right? It's all sort of a knowledge-y kind of stuff. There's a little bit of quantitativeness. You can put, you can quantify the properties, the isostrain, isostress. You can quantify bond length, wherever that was. Quantify chain length, right? But most of this is qualitative. This stuff up here is all quantitative.
I don't like the TTT diagram. Can we get rid of that?
No,
Can we please get rid of that?
no. So you've got a big chunk. You notice I said here, thermal properties, this is the biggest area of focus in this section. We had 2 chapters, right? 8, 9, 10, 11, 12. We have 5 chapters that we're covering. 2 of them are on thermal properties. So you know you're going to get more than just a single question on thermal properties. Okay. So you got to be able to know and interpret the phase diagrams.
So interpreting phase diagrams, that would be considered quantitative?
Yes, because you're going to quantitatively interpret that. Right, if I throw up a, let me see, Chapter 8, I think, is the one that has phase diagrams. Nope. Chapter 9. Right, so we have the phase diagram, so here's lead tin, for instance, right, let's zoom that out. So on the lead tin, I don't have my little pointing stick and it's gone.
Oh, no.
All right, so I'll have to stand here and use my finger. All right, so it's quantitative because anything you measure on here is somehow quantitative. So in other words, if I say I've got a 70% solution at a certain temperature, whatever temperature that is, 100 degrees C, you've got to be able to tell me what percentage of it is beta and what percentage of it is alpha, right? And you got to tell me, you got to be able to identify the concentration of the beta and the concentration of the alpha, and it's all quantitative. Does that make sense?
We don't have to memorize any values for these charts.
No, I'll give it to you.
What kind of things should we be looking at that would be important to memorize? Like any key equations that you could hint us on, or?
So, I'll give you, yeah, I guess I didn't put that on there. I can give you the equation sheet, the sheet that I'm going to give you.
Okay.
So anything that's not on there that you think is important is what you need to do. So I'm not going to, I will tell you, I told you the other day, I'll give you the isostress and isostrain equations. But I won't tell you which is isostress and which is isostrain. If it's on you to remember. I will not give you the inverse lever rule. You need to know the inverse lever rule. Okay. So it'll be all the same equations I used the first time, plus a few more. But only a few. Okay, so the phase diagrams. You got to be able to distinguish what kinds of phases are present in each region. So what that means is I gotta know this is alpha, without the labels, right? Because this one's labeled, without the labels. You gotta be able to identify, this would be alpha lead, this would be liquid, this would be alpha plus beta, this would be beta, beta plus liquid, and alpha plus liquid. Right, you need to be able to identify what two phases are present. in
Right, so
each
we
one.
need to know that for that particular
For
kind of
any-
diagram,
For that,
that it's alpha and beta over there.
yeah, just call it alpha and beta, alpha, that's sort of the generic.
Oh, okay.
So the point is you need to know that this is a solid solution,
Oh, okay. So we don't have
alpha,
to
this
know
is a
exactly
solid
what it
solution,
is.
call it beta,
Okay.
right? You don't have to know that they're specifically alpha or beta, but just that this is a solid solution, whereas this region is a mixture of two different solid solutions. No, what's that?
Or you need to know every, like, in the ones that is the iron carbon one that has like several spots to it, or you need to know that one as well.
Wait a second, one second. I'm long. So that one? No, that's not it. That's it, that iron carbon. So you would have to know, again, that this is, you probably, for iron, you should know the names. You should know that this is alpha ferrite, this is gamma austenite. Don't worry about delta, nobody really uses delta. But these two you should know. You know that's Fe3C or cementite. You know, those things you should know because steel is just too important a material not to know this, yeah.
So are we gonna need to know like the different temperatures?
No, I'll give you that information. You just need to know, I mean, you probably should know this one, honestly. I'm not gonna require you to, but I'm just saying you should know that just as a matter of, one thing one piece of knowledge you should retain for future use. So yeah, there's some, this one, more than any other, is the one you should know the numbers for. But I'm not going to make you recall numbers in order to solve the problems, right? Because you have to have the whole diagram in order to be able to do much of anything. But you got to be able to identify what phases are present in each of those regions. Okay. Next, you need to know various special features: eutectic, eutectoid, paratectic, paratectoid, all those sort of things. Okay. Again, that's kind of related to the vocabulary at the beginning. But you need to know what they're. If I show you one, you need to be able to tell me, oh, that's a eutectic or eutectoid or whatever. Or you've got to be able to identify, identify them on the graph. Describe the characteristics of each phase. So you got to tell me. You got to be able to tell me if I have 1 kilogram of this stuff. Right, and I go back to let's go back to this one because it's simpler. 1 kilogram of 30 weight percent tin, you've got to be able to tell me not only that this is liquid plus alpha, and this is alpha plus beta, but you've got to be able to tell me how much, if I have 1 kilogram, how many grams of alpha do I have, and how many grams of liquid do I have, right there. Right, you've got to be able to tell me the amount of each phase. The composition of each phase. You got to be able to tell me then that this, we're taking 30 weight percent tin at 200 degrees. That the alpha that is present at this point has a composition of 17 weight percent tin, and the liquid that is present at this point has a composition of 55 weight percent tin. See what I'm saying when I ask for the composition? And then the microstructure. So you got to be able to tell me what this looks like by drawing one of those microstructure diagrams. Right, so a little square with what you would see in a microscope kind of thing. Okay, you got to be able to draw that for me. And if we did that at 100 degrees, what would I see?
Alpha with beta.
I would not see alpha with beta around.
What composition are you doing?
30 weight percent, cooled down to 100 degrees C. What would I see?
So you would see alpha particles with beta in between?
You see alpha.
Isn't this one a little tiny?
Right, I would see alpha particles, and in between that, I would see my eutectic lamellar structure, right? You see what I'm talking about there? So in other words, as this thing cooled, at the instant, right before it went through the eutectic, it had a certain amount of pro-eutectic alpha, right, alpha that had formed before going through the eutectic temperature, and the rest was liquid. But immediately upon cooling to below 183 degrees, my alpha didn't change, but my liquid now all solidified into a eutectic microstructure, pearlite, right, the lamellar structure.
But that solid compound is beta.
That lamellar structure is a mixture of alpha and beta, right? The stripes, one's alpha, one's beta, one's alpha, one's beta, that's where you get the stripes.
So that's, if it were to be a higher weight percentage, then it would move towards being more even stripes. Like,
So it's
not
it-
fat alpha and skinny beta, it would be.
Yeah, but I'm not gonna
Okay.
hold you accountable for that. Just the fact that it's, you know that it's this pearlitic or the lamellar eutectic composition or microstructure.
So, but you'd still use the lever rule to find out how much beta there is.
You'd still find out, yes, if you want to know how much beta is in this, you would still use the inverse lever rule to find how much beta is in
That's
it.
only the
But all the
beta
beta would
stripes.
be distributed throughout this lamellar structure. And if you find out how much alpha there is, then there would be alpha, some of the alpha would be here in these big chunks, in the proeutectic alpha, and the rest of it would be buried in the lamellar structure.
Now, as that temperature cools even further closer to zero, the straight alpha particles are gonna get smaller and smaller, correct?
Correct. It will be absorbed back into the you know, the mixture stuff, and the beta stuff. You know, your beta bands in here will get have less and less tin.
But it's still gonna have that, you take the,
Lamellar structure.
But it'll still have
the
lamellar structure, correct.
Right. Okay, so we're not worried about exactly, you know, what the change in the thickness of lines. You don't have to worry about that. It's just the distribution. How much of it is was eutectic material? How much of it was pro-eutectic material? Does that make sense in terms of what I'm asking for on those? Okay.
And what's the structure when it goes right through that minimum point?
Right through the eutectic?
Yeah.
It's all lamellar.
Okay.
Okay. Now, how to use the inverse lever rule, again. Be able to describe the evolution of microstructures as you cool down the phase diagram, so kind of like what we were just talking about. Be able to show what happens if I cool from here down, right, I form some alpha, then it's all alpha, and then what happens as I start to get down here?
Beta forms at the boundaries.
Right, beta forms at the grain boundaries, right? So you gotta be.
So
able-
whenever you cool down so that you're passing the eutectic point and you're not in one of the solids, then you are gonna get the lamellar stuff.
Right, if I'm out here, if I'm anywhere between 19 and 97.5 on this diagram, I would get some lamellar structure. Yes,
Right through the eutectic point, you get pure lamellar though.
that's what he just asked.
Oh,
Silly goose.
But the answer is still yes.
sweet.
But the answer
So yeah, second time.
Okay. Okay, and again, be particularly familiar with the iron-carbon phase diagram. You know, so again, knowing alpha or austenite, some ferrite, those sorts of things. The TTT diagram. So now I'm going to have to go and open another. Let's go back here.
That's the next to say me.
TTT, I think was chapter 10. Yeah. Okay, so TTT diagram. So in the TTT diagram, you need to be able to describe the resulting microstructure when a given cooling quenching history is provided. So if I give you that, or that, or that, you gotta be able to tell me, what's the microstructure gonna look like.
Can you go back to the green one? What exactly, I feel like these ones, cause it isn't like, just like a straight over and then down kind of thing.
Yeah, I won't, if I give you curves on a TTT diagram, I'll make them straight lines, even though
Okay.
that's not realistic.
So this one, but this one, what would you say, I guess what point would you average it to be?
So what would you tell me that is?
Course per light.
Right, so 100% course per light.
But, and that's because it crosses all the way through the 100% in the course per light category.
Right, so, in other words, if I instead said it came over here, if it came down here, over to this line, or let's see, how would I do that? If I came over, pulled down here, let's just go to the knee. I went to the knee here, and then stopped at the 50, and then cooled down to here, and then went the rest of the way over. That would be 50% fine perlite, and then the rest would be bainite.
Okay.
Right, so you get as much as you get from the first time through, and then the other 50%,
Once you finish it.
you can't finish until you get it,
So in this case, since it goes all the way to the 100% curve, the one on the right,
Right, so
in
you're
the
gonna
course
get,
per light region.
you're gonna get perlite of ranging coarseness between these 2 points, between these 2 levels, but they're both coarse perlite. So you just say it's 100% coarse perlite. Okay.
So if we did that same thing where we went to like 50% fine or light, and then we just went straight down, the rest would be martensite?
Yep.
So they're like an exact transition point from coarse perlite to fine perlite to bainite?
Nope.
Okay, it's just kind of, so like, if wherever like in that middle-ish area, you just kind of like somewhere in between coarse and fine perlite. Something.
What's that?
And how do you know if it's like right there in the middle, how do you know if it's coarse perlite?
So it's my job to make sure that I don't put you right in the middle.
So if it's right in the middle, we probably it's been wrong.
Right. So, and I will tell you, if I tell you, you quench to a certain temperature, then you hold it for a certain amount of time, then you quench to a certain temperature, all that kind of stuff, right? Like I gave you descriptions in class, draw all your lines vertically. You quench, you hold, you quench, you hold. Okay? Just assume that everything's vertical and horizontal.
So will the TTT
Yes.
diagrams always be just the iron, the ferrous compounds? Basically this one,
Not necessarily.
because we never really work with any other TTT.
Well, but the concepts are still the same.
But you would.
But you need to know this one. This, again, steel is the one you need to know.
But you would label it, you would label.
Well, if it were steel, I wouldn't label it, because you need to know coarse perlite, fine perlite, and bainite,
Yeah.
right? If it were some other thing, if I made up some, gobbledygook kind of, material, then I'd have to.
But
give
you would
that
have the
information.
curve drawn in there, wouldn't
I would have the curve drawn, right, so you'd have to work with the curve.
So we have to draw the curve for this
No.
one. Okay.
You might have to draw the temperature histories. Right, the heat treatment, but you wouldn't have to draw the actual curve. You see what I'm saying? You have to draw the quench, leave it,
Oh,
quench,
yeah,
leave
yeah,
it,
yeah, yeah,
but
yeah.
not the actual curve.
I thought you were gonna have to label like all the temperatures.
No.
We're gonna try to recreate it.
Okay? Everybody good with that? What else? Quenching history. Be able to describe the necessary cooling and quenching history required to obtain a particular microstructure. So you need to be able to go both ways. Right? If I give you a quenching history, tell me what microstructure came. If I said I want, 75% bainite and 25% fine fine perlite, you need to tell me what temperature history is going to be necessary to get that. Okay. Understand the effects of various heat treatments. Remember, we then talked about the idea of tempered martensite or tempered bainite, or the various different things we could do, right?
Did you ever do,
So then you need to understand those effects.
tempered perlite?
No. And be able to describe the heat treatment required to achieve that desired microstructure. So again, if I told you I wanted to have 50% fine perlite and 50% tempered martensite, you'd have to show me the process to get that. Okay? Kind of working backwards through this, but. And then the last thing is the mechanical properties, which is actually the first thing that we talked about. And it was all primarily fracture and fatigue. So you need to be able to, yes, sir.
Will we get equations for those, or do we need to know?
I will give you the Griffith sharp crack criterion, sigma equals sigma max square root of, that square root of the ratio of the crack length and crack tip radius of curvature. So I'll give you that. I don't think I give you anything else.
That's only.
No, I'll send out, after we're done here, I'll send out the equation sheet that I'll give you. Same, fracture mechanics, so you need to be able to understand how cracks amplify stress. Fatigue, the process of cycling, and you need to understand what that means in terms of use, especially as it relates to sort of design problems. Okay, so in other words, if I told you needed to design a material for a spring that's going to bounce 100 times a second for however long, then you got to be able to understand how to use that, use a fatigue curve to be able to design around that.
It's a really fast spring.
Whatever. And then qualitatively, be aware of the NDE techniques. So there was some quantitative NDE stuff, like ultrasound on the homework. So you don't have to worry about being quantitative with the NDE, but you should be qualitative. And obviously, this is way more stuff than I can put on the test.
But if we know
So-
this,
But if you know all this
So
stuff.
which ones of these things then not gonna be?
You give us 2 letters that won't be on the test.
Z and Q.
That's
No zinc.
Okay. So that's sort of the walkthrough. So like I said, the first half is quantitative, the thermal and mechanical stuff is very quantitative. The last stuff is more qualitative. But there's still some quantitative stuff at the end, and there's still some qualitative stuff at the beginning. So you can't just sort of divide it exclusively.
it's kind of random, but I know you said last time you gave the first test, or the first time you gave the last test, it was like at your old school, it was like a 90% average. Do you remember what it was for this?
I have no idea.
It wasn't, no, the old school.
No, the
Last
old school
year-
was actually worse than that. Yeah, last year, the 90% was the first time I taught it here at Taylor.
Oh, so you taught this year?
Yeah, yeah. But the old school stuff was actually IIT. I didn't teach this at my last job. I taught it at Illinois Institute of Technology in Chicago. And generally speaking, the average there was lower, but it was in a different order. So, like I said, I've told you before, the book, he changed completely the order in which he did, laid out the book. So there are parts, there's no real direct comparison. There's parts of the beginning were at the end and parts at the end at the beginning. Yeah, so but I don't know how everybody does.
It's just a random question.
I don't know.
Just gotta keep-
I can look it up if you want to stop by my office. Any other questions?
How has your week been?
No. Material science question.
I do have one, and it's not incredibly related, but can you cold work wood?
Can you cold work wood?
As in, if you like run it through a roller, right, does it have the same effect as?
No. Because the deformation mechanisms in wood are different. They're not. Wood does not experience dislocation propagation. So,
You
So-
can harden wood, right? Somehow heating it up or burning it or.
so I'm sure wood has a certain amount of water in it. It has a certain amount of I mean it's a polymer. Basically cellulose is the main component of it is a polymer. So and I think cellulose is a thermosetting polymer, so you can probably develop cross-linking and something if you heat treat. You might be able to treat wood. But I honestly haven't studied it, so I don't know. 5 in homework 8. Sure, I know number 5 in homework 8 off the top of my head. Let me, I'm not gonna be able to do this without you guys seeing anything you're not supposed to see.
We
Yeah,
could have someone else.
I can do it. No
I
problem.
can close our eyes.
You're peeking.
Homework 8, I will preview quiz,
What?
number 5. Oh, yeah, the P205 density, the particles.
Cool, thank you.
Okay. So the key here is to translate from weight percent to volume percent. We're given 3.7 weight percent P205. And we have to transfer that into a volume percent. Because then then we can find the volume of each part. So I don't have the numbers off the top of my head. Anybody remember the molecular weight of P205? What's
It's
that?
141, I think.
It's 141, I think.
Yep.
Well, I think you just-
16 times
Okay, what about the other thing? The lithium, aluminum, silicon, glass.
238.
What is it?
230.
Oh, you're just making numbers up. Nobody remembers?
Austin is looking it up.
Okay.
Oh, wait, that one's.
We're counting on him. But he's
Just being slow.
He's being thorough.
It's very well organized.
Nothing's seen.
I thought this guy had,
Did you not use it? Did you solve the problem?
Really, we don't know.
Yeah, I never used that either.
All right, I'll look.
Okay.
I'll use
That's fine.
mine.
No, that's fine, that's fine.
No, I got it, really.
So you assume, let's say you have 1 kilogram of material. So you have 1 kilogram, that means I have 37 grams of P205.
Right.
And its density is 2.39
yeah, no, you don't.
grams per cubic centimeter,
Well, I think it's 100.
or megagrams per cubic meter. Okay.
It's 141.95.
Okay. So 37 grams of P205, and that's the density. So if I know, then I take if I know that, then I take 37, and I divide it by 2.39, and I'm going to use grams per cubic centimeter, because I really prefer to use common numbers. Okay? And I end up figuring out how many cubic centimeters of that I have. Anybody got that? Nobody? So I can find out how many cubic centimeters of P205 I have in my 1 kilogram of stuff.
15.4.
15.48
11715.
cubic centimeters, good enough. The other stuff, I've got 963 grams of the other stuff, and its density is, what is it, 2.85?
96.3.
Yeah.
2.85? Divided by 2.85. And what was that?
Isn't it 96.3 and 963?
Yeah, but I said I'm going to take 1 kilogram.
Oh.
So I'm just using it as a sort of a constant. So what is that?
337.9.
337.9 cubic centimeters. Okay? Does that make sense?
Yes.
Okay. So now my volume percent of the P203, or P205, is going to be 15.48 divided by 15.48 plus 37.9. And what is that? Anybody? Someone? Anyone? Bueller?
Got 0.0438.
0.0438. Okay? So, now that I know the volume percent, I can take my 1 cubic millimeter. And it said that there are 10 to the 12, is that right, 10 to the 12
Yes.
particles per 1 cubic millimeter, right? So that means that there are 10 to the of solid, you know, the whole thing. That means there's 10 to the 12 particles per 0.0438 cubic millimeters of P2O5. That make sense? So that 10 to the 12 particles is distributed evenly among 0.0438 cubic millimeters of P2O5. Or the other way to look at it is that the volume of a particle is 0.0438 divided by 10 to the 12, or 4.38 times 10 to the minus 14 millimeters. That's the volume of the particle. Now that I know the volume of the particle, I can set that equal to 4/3 pi r cubed, solve for r, and then double it to get the diameter, which is the particle size.
Wait, hang on.
What? You have different numbers?
It seems like times 10 minus 14 cubic millimeters is too small.
That would be times 10 to the
Wow,
minus
what's the
23rd
cube root
cubic
of that?
millimeter.
Is
10 to the minus 5.
yeah, so that's right.
Yeah. Does that help answer your question?
Directly answer.
Well, I didn't get to the R.
Is the camera on?
Yes, it is. I think so. If not,
Well, because it was
Sorry,
I didn't know.
oh, did it beep really?
No, I mean, it was, and you said, don't worry about it, I don't know if you
Oh,
want.
you're right, I probably forgot to start it again. We'll check, just make sure.
I think he's doing it.
Oh, yeah, it's blinking. Dan's good. All right.
Hi, Dan.
So we didn't need the atomic mass.
No, I forgot that they had included density, so I was gonna get the density from the atomic mass. That's why I was starting that out rather than remember that it had the density.
How did you remember?
Why did I remember
Just got it.
Was it really 141?
that? Yeah.
Yeah.
Oh.
Every single molecular compound is
Maybe
just.
throw another.
It's like a random superpower, the ability to remember the atomic mass of any given compound.
That'd actually be really helpful this semester.
Oh, yeah. Taking-
All right, anything else?
Chemistry in this class.
Anything else material science related?
Anything unrelated?
Well, yeah. If it's unmaterial science
Yes,
related.
you want to
don't
make.
worry. What is the airflight speed?
I guess be velocity, but I'm late to swallow.
I freaking swallow a European swallow.
I don't know.
What do you know these?
All right.
You know all sorts of words.
Sorry.
Okay, I apologize for that.
You know?
Nothing? Nothing else?
Just
Viewers.
All right then. So, study hard. I assume we'll do the test on Tuesday next week,
I
correct?
can't take it Monday.
Oh!
So,
No, it curved, it was a bad shit. It's a bad shit. You trying to shoot him there? Yeah, I was looking.
seemed to go pretty straight for me, I don't know.
Back in this video. Here's the
It's not like time between class and shoot, remember?
Right, right.
So Tuesday, are we taking the test Tuesday? Everybody's on board for Tuesday?
I can't take it Monday.
Yeah, I might potentially take
I don't
it.
have a.
I just said Tuesday and you're telling me I can't. I can't take it on Thursday, so.
Well, I'm saying
It's irrelevant to my question about Tuesday, but thank you for sharing.
it has to be Tuesday because I can't take it Monday.
Tuesday is okay for everyone, sometime between the hours of 8 AM and 5 PM. You have 2 hours to take the test.
Are we allowed to take it on Monday?
If, let's see, are you allowed to take it on Monday? Yeah, if you can work around my schedule, I mean, I have many classes on Monday, so.
Materials is canceled though, right?
I just need a way
Right,
to
there's
get
no
on
materials
vacation.
class on Monday, so you could do it during materials class in the hour after if you wanted to. You can do it from 3 to 5, for instance.
Okay.
But just let me know.
When do
Otherwise-
we need to let you know for that? Like,
If you want to take it on Monday?
Yeah.
Probably by Monday morning, so I get the test
Okay.
printed. So, okay?
Yes.
All right.
I think what happened was, I was trying to do like this, and air.
Oh, yeah.
No, it's just like, you know, it's the aerodynamics.
It's the airspeed velocity of the water bottle, isn't it?
Come back or stay here?
It's just, you can't throw.